Dobré ráno, vítám vás na dalším webináři, který se týká Altium Designeru a dneska je zaměřený na simulace plošných spojů a proběhne trošku neobvyklou formou. Já budu jako host vlastně vás tady provázet, nebo spíš jako moderátor a pozval jsem tady pro vás na toto téma kolegy z firem Advanced Engineering a z Altairu. První z nich je Tomáš Čurda, který vlastně má na starosti business development v rámci České republiky a nástrojů právě i od Altairu. A v podstatě cokoliv, co by vás zajímalo ohledně toho tady v České republice, tak se můžete obracet na něj. Dobrý den.
Jen.
A jako druhý je tady s náma aplikační inženýr Marek Jableka z Altairu, který nám potom v té další části ukáže přímo demo, jakým způsobem Altair PollEx jde používat. Hi Marek,
Ahoj, hello, dobrý den.
dobrý den. Tak to do začátku na představení. Co vás dneska čeká? Vidíte v trošku jiné složení, že nás tady bude víc. Do začátku bychom chtěli říct představení vlastně, z jaké pozice vám ty věci budeme ukazovat. Po tom krátkém představení vlastně už máme naplánovaný to, na co jsme vás zvali, to znamená simulace ohledně signálové integrity, simulace napájecích cest, termální simulace v takové základní podobě a na závěr nějaké ukázky, co dalšího PollEx dokáže pro validaci plošných spojů pro výrobu a pak si to všechno shrneme. Do začátku bych hrozně rád věděl, jakým způsobem u vás provádíte simulace plošných spojů, tak jsme si pro vás připravili takový krátký dotazník. Tak budeme rádi, když nám dáte vědět, aby jsme měli představu, jaký s tím máte už doteďka zkušenosti. A k tomu představení, já bych tady jenom krátce řekl, že za nás, za vlastně Retry, nebo už se tady setkáváme na těch webinářích poměrně pravidelně, tak toho nechci říkat nějak extra moc, ale v podstatě už na začátku letošního roku jsme oznámili, že se postupně budeme spojovat se skupinou Computer Controls, která nás který vlastně proběhla akvizice naší firmy už v roce 2021, takže nás postupně uvidíte měnit trošku vizáž a tak podobně, ale všechno ostatní zůstává stejný a pro ty z vás, který jste se značkou Computer Controls doteď nepotkali, tak možná bude známější dřívější jméno HT Eurep, který vlastně používala Computer Controls v České republice dřív. Computer Controls je skupina, která operuje v této části Evropy, jak vidíte na té tabulce nebo na té mapě a hlavní centrála je ve Švýcarsku, odkud se všechno řídí a v každém státu máme pobočku, která se stará o některé nebo o všechny obory naše. Konkrétně se skupina zajímá o telekomunikační služby, prodej součástek, měřících přístrojů, obecně softwaru pro elektroniku a dodávání služeb. My tady v Česku jsme zaměřený na prodej elektronických součástek, to, co vlastně dřív dělal HT Eurep, tak to vlastně zprostředkováváme nově z naší pobočky v Brně a samozřejmě software v podobě produktů Altium a v podstatě tím jsou potom pokryty i služby, které vlastně s tím právě souvisí s tím, jak se softwarem, tak s těma komponentama. Tak, to je z mé strany všechno na ten krátký úvod. Předávám slovo panu Čurdovi, který by vám řekl nějaké základní informace o Advanced Engineering a o Altairu.
Dobrý den. Jenom se ujistím, že vidíte moji
Ano,
obrazovku.
všechno v
Děkuju.
pořádku.
Takže moje jméno je Tomáš Čvorda, jsem z Advanced Engineering. Ještě jednou děkujeme za možnost takového setkání s vámi. Jsem tady v tandemu s Markem Jablekou z Altairu, který vlastně bude mít dneska téměř celé to povídání na triku, protože chceme mít pro vás technický webinář, ale tak jenom, abyste tušili, kdo jsme, co jsme v Advanced Engineering, tak jsme za prvé engineeringová firma, která se zabývá výhradně simulacema a jsme taky zároveň lokální zastoupení firmy Altair v Čechách a i na Slovensku. Nebudu dlouho zdržovat. V oblasti nějakých výpočtů, simulací, pomoci se na nás můžete obrátit spíš v takových těch strojařských aplikací, to znamená, když byste potřebovali pomoc s nějakým casingem odolnosti, vibracema, nebo odolnosti vůči nárazům, tak to je to, co my děláme. A samozřejmě nějaké vystužování, optimalizace a odlehčování, to jsou ty parkety, kde se můžeme potkat. Samozřejmě i termální úlohy, to znamená, pokud byste chtěli nějak detailně řešit chlazení, větrání v rámci těch vašich zařízení, tak to je to, co my děláme. A technologicky ve spolupráci s Altairem vlastně zastřešujeme širší oblast simulací, o kterých se právě dneska budeme bavit. Jenom tak pro připomenutí, kdo Altair nezná, je to vlastně jedna z největších firm, která se věnuje simulacím, se sídlem v Detroitu nebo u Detroitu v Detroit a vlastně vyrostla na simulačních technologiích, na preprocessingu, postprocesingu, kde vlastně byla jakoby nejsilnější na trhu a dneska to její portfolio nejenže zaobírá veškeré možné fyzikální simulace, ale v podstatě i zpracování nějakých datových analýz, které se začínají v podobě strojové učení a umělé inteligence prolínat s tou klasickou numerickou formou simulací. A dále jsou tam aplikace pro IoT, pro vysokovýkonné výpočty a další specializované aplikace. Od Altairu můžete čekat modelování a simulace na systémové úrovni, kdybyste vlastně dělali nějaký celek od řízeného systému, řídícího systému, kombinované elektrické, pneumatické, hydraulické, mechanické systémy, to všechno dohromady. Simulace jednotlivých fyzik, to znamená mechanika, teplo, proudění, elektromagnetismus a tak dále a tak dále. A taky ověřování vyrobitelnosti. I tomu se vlastně budeme věnovat dnešním povídání, který bude zaměřený právě na tu vaši oblast elektrotechniky a elektroniky. Takže termální simulace, pokročilé multifyzikální simulace, strukturální analýzy, optimalizace, to jsou ty témata, které jsou pro Altair typické a také ty vám blížší třeba simulace elektromagnetických polí, když navrhujete antény, chcete, aby měla co nejlepší parametry, jejich správné rozmístění, pokrytí signálem, a tak dále. Co se týče vlastně vývoje elektronických systémů, tak my vlastně jakoby navazujeme na elektronické CADy, takže Altium Designer je takový ten asi nejbližší případ, kde je největší integrace a dále vlastně jsou to termální simulace nebo simulace pro návrh napájení výkonové elektroniky a třeba i návrh silikonových, křemíkových a polovodičových prvků. Takže my se budeme v tom workflow nebo v těch disciplínách věnovat dneska hlavně vlastně ověřování návrhu PCB desek a já nebudu dlouho zdržovat a předám slovo kolegovi Markovi Jablekovi z Altairu.
Děkujeme moc krát za představení and stage is your, Marek.
Okay, thank you.
Maybe just a second regarding the language for the audience. Další část vlastně bude v angličtině, tak jak jsme avizovali v pozvánce. Dotazy můžete posílat, jak je vám libo v angličtině, v češtině. Budeme se snažit to, že většina bude na Marka, tak se budeme snažit je pro něj přeložit. Thank you. And that's
Super,
it.
thanks. I know a little bit Czech, but it's not so good to answer your questions. Okay, so let me start with some short introduction on the electronic tools or the tools from Altair that helps the electronic designers in their everyday job. So I will try to share screen, and I hope you can see a white screen with nothing. So it should be okay.
Yes.
This is video player. Okay, so I would like to guide you through a very short 2-minute video that shows the drone aspects, elements, and the design, because this is a multi-physics solution. And I will just talk a little bit about the elements or the sub-tools of Altair portfolio. We have more than 180 tools in Altair. So this is really a big number, and many of them is dedicated for electronics. So I would like to just give you a brief overview what can be done using Altair tools for electronic design. So let's start the video. First of all, when you design the electronics, you need to have a kind of a silicon chip. So we have a silicon debugging tools acquired 1 or 2 years ago. And also with the Simla platform, you can simulate the 3D topics around the chip and around the silicon. So the thermal mechanical topics. And then we go to the entire PCB, which is actually the scope of this webinar and the meeting. And the tool called PollEx will be the main topic here. And in PollEx, you can check the electrical design, you can check the assembly problems, you can as well check the manufacturability of your product, some kind of collisions between the parts, and many, many other aspects. The main focus for today would be, of course, the simulation, so signal integrity, digital communication between the components on the board, as well as qualification of the PCB against the power integrity topics. PollEx has some basic thermal simulation capabilities, but the main tool for thermal simulation is SimLab, which allows to full CFD, 3D thermal analysis in the time domain, not only the static. When you assemble the product like here, you of course have a lot of wires and harness. So we have a tools to inspect the wire harness, which is called eVision. And for a system level simulation, like you can see PSIM or the Twin Activate, which allows you to see entire product. Moreover, in PSIM and Embed, we allow users to generate the embedded code for microprocessors in a graphical mode. And of course, in this kind of systems, you also have magnetic circuits, especially electric motors. So for this kind of solutions, we also have our own simulator, which is called Flux and Flux Motor. For the entire product, you might need to optimize the full product. So for that, we use HyperStudy and some artificial intelligence tools from Altair, like RapidMiner. Of course, drone needs to communicate to the outer world, so to design antennas or to analyze the electromagnetic field around the product, you can easily use Altair FECO for that. And the last thing, the communication between multiple products, multiple drones, multiple devices, we have a tool called WinProp. To learn more about Altair tools for electronics, just visit altair.com/electronic systems design. And now we will just move directly to the topic. So we will move to the connection between the Altium and Altair PollEx. So I will show you how to deal with the PCB boards and how to run simulations on top of your PCB board to improve its operation. So to do that, let me share my screen once more, switch off these video topics, and you should see my screen with a very familiar for you application called Altium Designer. I hope we can start from here because you exactly know where we are and what it is. We are in Altium Designer. One thing that you might see here as a new menu at the top, it's the Altair PollEx. Maybe I will just ask if you can see the screen. I hope it's
Yes, it's
okay. Super.
working.
So you can see the new menu, which is called Altair PollEx. It's super easy to install. You just go to the extensions and updates, and you find Altair, and you can install this add-on fully free of charge. And with that, you can easily get the design from Altium Designer to Altair PollEx. I will click it, and it will just work in the background. So this is one of the methods to get the design from Altium to PollEx, the easiest one. You can also go with the design to PollEx, just saving the design as the ASCII file. Sorry, it's something that's happening in the background. So you can save the design as ASCII file. It has to be ASCII. It cannot be this encrypted file. We are working very closely with Altium to quite soon have also the ability to open each and every type of the file from Altium Designer. And the last method to get the design to PollEx is just to use the ODB++ format. There's an add-on for Altium that you can install, and you can also export ODB++ and get the data into PollEx. And then when PollEx opens, the design is there in PollEx, so you can continue working in PollEx. As I mentioned, it opens multiple formats. We are here interested in Altium, but if you are running a company that is using multiple ECAD systems and you need to import multiple types of the boards, so you can see PollEx can import really each and every format on the market: Altium, Cadence, Zuken, ODB++, Eagle format. So all the formats that the ECAD engineers uses in their everyday job. Good. So we are with this PCB board in PollEx, and what we can do with this board, we can review the layers. We can see this is just a 6-layer board. First layer, it's just some parts and interconnections on this sample board. The second layer is the ground plane, so the area where the return currents go back to the source. Then on the third layer, we also have some interconnections, mainly for high-speed interfaces like DDRs. Fourth layer is very similar to the third, so also a lot of interconnections, and the rest is just a ground. Layer number 5, it's a lot of power islands, so elements that just delivers the energy to the chips. And layer number 6, it's also component placement, paths, and also some kind of routing. I'm focused on the layers because typically the first thing what people do after importing the design is to review and manage the layer stackup. It's a kind of mandatory step for to begin the simulation in the simulators like PollEx or the other 2.5D simulators on the market. You need to tell the simulator on which layers there are the reference planes, on which layers we just run the signals, and where are the this kind of connections. So we can see it's a standard stack-up definition, like everywhere in most of the tools. You can play with the materials. You can change the materials to something else to conduct what we call in the simulation area what if analysis. What will happen if I will change the PCB vendor from company A to company B, and they have a little bit different stack up, different machinery. So you can play with this data, with materials, a little bit with the thickness as well. You can, of course, create your own library of the stack ups and import this stack up to this tool to find out how this will impact the outcomes of the simulation or the analysis. But the most important, what an engineer needs to do is to set up the reference planes, the planes through which the current will have the return path to the source. So we'll just set up the second and the fifth layer as ground and power. I will just save it as the project PRG to save all of this data together with the with this PDBB file, this native format of Altair. Good. So stack up is done. This is halfway to start the first simulations. One other thing which is available through PollEx is the ability to segment the design into a specific interfaces. I know that there's a lot of questions if we can import the this kind of naming conventions from Altium. I would answer that already here. We are not yet there. We have our own Altair methodology here implemented, so we can create something like a regular expression language because we support so many ECAD systems. So it would be really hard to tie together all the naming convention approaches from Cadence, Altium, Mentor, Zuken, and all of that. So at this moment, we work on this kind of approach that you can define your own naming conventions that you use in the company with very simple regular expression language. You can add some new filters to find out the nets, and automatically with this regular expression filters, PollEx is able to detect what kind of nets you use inside of your design. So you just find the net class, and you can see PollEx automatically knows which are the power nets, the basis of its name, which are the kind of high-speed interface nets, so the signal nets. So this is the net detection. We will come back here for some other setups while doing power integrity in a second. And the last thing which needs to be done in the PollEx before doing any kind of simulation and analysis, it's the parts, and it's also quite important topic for the people doing simulation, signal, power integrity simulation. This is the information about models, about the components, about the parts used in your design, in your simulation. There are a couple ways to get the parts library in place. The easiest way, when you use PollEx often, you build your own library, you build your own list of components covered with the models. So the easiest way is just to synchronize with the specific library that you have created inside your company. It will just fill in the missing data. But to do it once upon a time, or to do it not so often, sometimes you just need to do it manually. So I will just show you what is possible in PollEx, how we can set up any model. Let's pick up the NXP microprocessor, 513 pins. So for that component, normally when there is no model here, it will be completely empty. So we will just see the pin number and nothing more for that device. But once we would apply the model, it will automatically fill in multiple information about this component. So we can, in Altair PollEx, use IBIS models. For smaller devices, we can use SPICE models. linear device. It's just representation of typical digital buffer, but just done manually, written what is the RDS on of the transistors, what are the slopes, and this kind of stuff. S parameter, Y, Z parameter, these are typical models for passive devices. If you want to have very precise wideband up to a few gigahertz, a wideband model of a capacitor, resistor, inductor, people typically use these SYZ parameter models. So for digital chip, which is NXP, we will use IBIS, and I will just pick up the CPU model. IBIS is read in. There are a few component solutions inside IBIS. I will just pick up the 513 pins, and you can see the signals from the IBIS model are attached. The models are attached. So then the simulation can be really started afterwards. Good. So we have models. We have segmentation of traces. We know that the stack-up is fully correct. So now what we can do, we can start doing some simulations and analysis. In the analysis menu, we have signal integrity, which we'll do in a second. We have SI Explorer. This is a kind of what-if analysis, pre-layout what-if analysis. So if you have an interface to design and you know what will be the stack up, but you would like to check if the length of the traces should be, I don't know, 10 millimeters or 12 millimeters maximum, or you would like to check if this is better to route the traces on the second or third or fifth layer. So this is SI Explorer. You just draw the schematic and you can do some simulations before even drawing the first layout elements. We have radiated emission. This tends to be a little bit misleading for many people. It's not the radiated emission from the PCB board. We use the PCB board, like here, as the source of the energy for the cables that are radiating the energy. So if you have a computer or a PCB that has a lot of cables connected to this device, so we can simulate in PollEx what are the shapes, what are the models of the signals generated to these cables, and then on the cables we can use Altair, which I mentioned on the movie, our electromagnetic solver, and we can see how these cables are radiating with the proper model of energy delivered by PCB. We are not yet, and I think most of the suppliers are not yet there to simulate entire PCB board as the source of the electromagnetic radiation, because the structure is super complicated. We would need to set up each and every model on the PCB, that each and every metal element would have the right potential, the right impedance to ground to create this entire huge complicated antenna, which is the PCB. So this is radiated emission. We also have power integrity, I will show it later, and some kind of static thermal simulation. This also will be shown in a couple of minutes. Good, so starting from signal integrity, this simulator is the 2.5D simulator. So what it does, it takes all the possibilities that you used on your PCB, so each and every trace width that you used on your PCB, and on the base of this standard structure, so the trace which has a width and length, PollEx can create a mathematical model of this connection and then turn it into a SPICE model. That's why 2.5D simulator provides you results in minutes, while the full 3D electromagnetic simulator, it's more accurate, but it provides you results in hours, because it will build a meshing, millions of triangles on top of the single net, which is really then takes hours to complete the simulation. So automatically what PollEx will do, it just finds the trace widths on a specific layers. We can create some models. And on the basis of this, for a specific model, PollEx can understand what is the impedance, what is the model of this piece of trace. We have here, for instance, 0.1 millimeter trace on the layer 1, reference to the layer 2. So it looks like this. We have the piece of trace on the layer 1. There is a reference plane on the layer 2. And on the basis of that, what PollEx is doing, it's creating a specific model for this kind of trace, and then you just multiply it by the length of the connection. This is all the 2.5D simulator magic. But this is very powerful. What you can do with 2.5D simulator, starting from the most simple analysis and very powerful for the electronic designer, ECAD designer, for instance, the crosstalk analysis. The crosstalk analysis will understand or give you the understanding what is the interaction between the traces in the PCB, what are the aggressors for a specific victim net, and what kind of nets can be aggressors for a specific net. How does it work? You as a user, you just set up the geometrical rules. So this kind of how long they should go in parallel, how big is the distance from the net where we really search for these aggressors, and some few other aspects. And you can see how fast this works for this kind of big board. We could find the strongest aggressor for a specific victim net, but then we can definitely go deeper into a specific net. So if we'll go to address line 7, we can see there is 1, 2, 3, 4, 5, 6, 7, 8, 9 aggressors which are interacting with this specific address 7 net. So we can actually even see here we have the victim net, and we can see that there is, for instance, address to aggressor. They have a very long parallel path in the PCB on these areas. So there is a danger of the crosstalk. We can also see some other nets. Some of them have a very short, let's say, interaction area. Some of them are very strongly coupled. But normally, this is a very good information for the very beginning, so we can understand what is the group of the aggressors that impact the victim net. To get even better picture, we would need to understand if the signal which is induced on the victim net is big enough to really impact the transmission. Because if we will induce, I don't know, 50 millivolts from all of these 7, 8 aggressors on the victim net, and this net is working with 5 volts digital signals, maybe with 1 kilohertz transmission, this 50 millivolts should not really be a case here, so we don't need to care. But when we want to have HDMI interface or some kind of 1.8 volts interface, this 50 millivolts can really be a headache for the transmission. So to understand how the aggressors are impacting the victim, in PollEx, you can really set a group of simulations. So just tell that one of the nets, for instance, is working on 833 megahertz, the other, I don't know, 250 megahertz. We have some low speed interfaces here, let's say. We have some 356, some kind of 1 gigahertz interfaces, etc. So with all of that, PollEx can give us the information how the aggressors are impacting the victim net, and can tell you if the signal induced on the victim net is really a dangerous one or is not a dangerous one. Yeah, but we don't see here. I think this is the problem of the models. But generally, the outcome of that is just the signal induced on the on this victim net. I will not repeat it due to the sake of time. I think I made a mistake with the model setup. So this is the crosstalk analysis, the first type of the analysis that can be done with PollEx. The next type of the analysis that can be really done with the PollEx is the group of the analysis that is done for a specific net. So in PollEx, we can select a kind of net like for instance, this address, let's say address 2. So this is the net which can be used. See, there's something wrong with the model, sorry. That's why the simulation did not work. Let me just maybe stop it and open it once more. Sorry for that. But due to this sake of time, I would not configure it once more. But let's run this simulation with some pre-configured model. So you can run the time domain simulation. You can run the TDRs simulation, and then multiple other simulations on top of your board. So once the models are set, you can pick up the traces for the simulation, which you would like to simulate. You have the ability to set up the driver pin. So on the trace, which integrated circuit is driving the net. And you can set up the frequency of operation for the net, like 233 here. And we have some specific IBIS models connected to the driver and to the loads or the receivers of the digital signal. And with that, what you can do, you can perform the time domain simulation. So just run a specific simulation for a period of time. You can run the frequency domain simulation, so extract S, Y, and Z parameters for this kind of net. So this is network parameter. You can run the time domain response, so we can shot a pulse to the line, and this energy will reflect from each and every discontinuity within the board. And this way you can see if your stability of the impedance in the connection is really good, or if you have a kind of via or maybe pad or a kind of component which is on the trace that could really impact the signal transmission, because the reflection energy, the energy reflected from that PCB structure is very high. So the signal is not going through the path, it's just going back to your source. And we have also I-diagram, which is mainly used for quite longer simulation, statistical as well, statistical eye. So this is used for the SERDES simulations. So the simulations where you include as well some kind of sequence of activities. It's used for IBIS AMI. So first you try to train your devices, so to understand what are the weaknesses of the channel. Then you adopt the filters at the ends. So in the transmitter receiver, pre-emphasis and de-emphasis filters, and then you start the simulation. I would not show it. This is very specific types of simulation and needs some really deeper knowledge about the transmission for the SERDES links. But this is what we got from the simulations. The simplest simulation outcome. We can see the transmitter part. and we can see the receiver part. We can see all these curves. This doesn't look super well, but yeah, we have some transmission and we have a lot of reflections. We have a lot of bad impact of the channel on the signal. What can be also done in PollEx, we can do some kind of measurements on top of these traces curves just to understand the distances, the delta, the values, the voltages, and all of that stuff. It can also be saved as an image, or the result data can be saved as the Excel file if you have any kind of, I don't know, post-processing approach, any kind of mathematical tool that you would like to use on top of the data. It's also possible in PollEx. What also PollEx does, it's the net topology. So if we pick up any trace, you can observe the geometry of the trace turned into a kind of a very simplistic schematic. So we set the driver for MCU microprocessor. Then we have a piece of trace with the length of 14 millimeters, which has the characteristic impedance of 49 ohms. And this is what I told you at the beginning. This is how PollEx is getting the model. It takes the trace with the width of 0.1 millimeters on the layer 1, reference to the layer 2, and then it multiplies that model by the 14.692 millimeters. Then there's a via model. Then there's a layer 6 piece of trace. Then there's another through-hole via. Then on the layer 4, there's a branch, another through-hole via. And on the layer 1, we go back to, these are probably memory chips. So this is a way to understand the elements of your design and also a place where you as a designer can really do some what if analysis. You can make some traces length to, I don't know, 25 millimeters. You can play with some, I don't know, components, like really destroy the signal, adding a capacitor somewhere on the path, and just play with the system to understand what is happening with your design. So we can have additional components somewhere, terminations, pull-up resistors, pull-down resistors, and many other things. This is actually this Signal Integrity Explorer, which I told you about at the very beginning. So you can do this analysis before doing any kind of layout, or really having the layout already done. So the trace is routed. You can still play with these traces, but not as an ECAD engineer, not changing the length, changing the profile of the connection, but as a signal integrity engineer, just playing with the parameters of the connections to find out what is happening. And from this tool, after applying all of these changes, you can as well run the simulation and see what is happening with your signal after applying this kind of changes to the design and to your layout. So this is the second thing. Oh, I closed PollEx, sorry. Okay. One other type of the analysis is the DDR analysis. So for this type of analysis, we can do the data line analysis, we can do the address line analysis, and we can do a complete DDR analysis. Honestly speaking, I would not run it right now in here because this is a very long analysis to be run, and it takes really sometimes up to 2 or 3 hours to complete. So but generally we set up the data lines. We can get them here, and then there is a very specific setup for the DDR analysis. If someone of you would like to do this kind of analysis, what you can do, you can go to our altair1.com website and just open the training there. So this is the altair1.com website. There's a training area, and when you search for PollEx, it will find for you some kind of pre-recorded classes training, and you can really follow the training to do this kind of analysis, to set up the analysis. What is very interesting in PollEx, you can really import the DDR specifications, so the JEDEC specification directly to your simulation, and it will set up the simulation, and then you can just run the simulation. So this is DDR. And with that, I would complete the signal integrity part here. Let me go forward to power integrity. So let's go to power integrity. For power integrity, the setup is more or less exactly the same. The only difference or the only information that we need to add on top of the configuration is for the parts. So for the components which we use in our design, you need to add the information about the power consumption. So if you read in the IBIS file model to your device, it will automatically tell that some of the traces or some of the pins have a pin type power, and there's a name of the power net which is used, VSSI or power or the others. And this information is then automatically passed to power rails in PollEx. Of course, if you have your own device and there is no IBIS model, it's super easy to create your own power domain for a specific nets. If you don't have IBIS, you can create your own power domain, and you will see it in this menu. And what is why I'm going to the component? Because from the component perspective in power integrity, we know how much current is taken from the source and what is the possible voltage drop that we allow for the device still to work correctly. So this is here. So all of the power pins, despite if there's 1 or 10 or 100, all of them together will consume, let's say, 10 amps. And we allow 100 millivolts voltage drop from the power rail to still be a safe margin for this device. So if there is a 10 power pins, this will be divided by 10, so each pin will consume 1 amp of current. This is the DC level power integrity analysis. The bottom part here is the AC level, so the frequency domain need of the component. So when the component is doing a lot of switching at a specific frequency, of course, the pull up or pull down transistors, they are pulling the current from the power line or pushing the current to the ground line, and with a specific slopes, with a specific frequency profile. And the vendors of the integrated circuits, they, in many cases, they tell that for this range of frequencies, you need to assure that there is, let's say, 100 milliohms impedance. For 100 megahertz to 300 megahertz, there needs to be a 300 milliohms of impedance. Of course, if there's a data sheet, you can easily give here, if your vendor tells for 400 to, I don't know, 150 megahertz, there needs to be half ohm impedance, so it can be set here very, very easily. So this is one part of the power integrity, to tell PollEx how much current each and every device component needs to draw from the source. The other part in PollEx is on the nets area. So if we have nets and their net type, net class is power, so we can edit power voltages and just fill in the table which tells what is the specific voltage for a specific line that we would like to analyze afterwards. This can also be exported to Excel. If you have your own databases, you can use VLOOKUP table, fill in the data, and then import it back with Excel. Super easy flow. If there's something else that you use to manage the current tree and the voltages information in your company. So with that, we can go to the power integrity analysis for the nets which are set as power, for the nets which are set as grounds. We would be able to pick up a specific net and start the analysis. I will just pick up something which is completed due to the time. So we had the core voltage net. There's a connector. The signal goes from one of the pins of the connector through some trace. Here on one of the layers, we have a lot of decoupling capacitors connected. There are some connections between the vias, and on the one of the internal layers, on the power layer, we have this kind of power island available. So with that, we set also the voltage for this line. So PollEx knows what's at the source. We set up the current consumption for each and every power domain. So we can run the DC drop analysis. And this analysis will tell us what is the current density in the copper, which is here, and what is the voltage drop to this device because of the routing we used for this design. So starting from the blue down to some yellow, we set up, I think, 1 something volts. But voltage like this, it's not very informative. It's better to observe the current density. So what is the amount of milliamp current per cross section of the trace? Where do we have any kind of hotspot? If we have kind of 5 or 10 or 15 amps per millimeter square, we need to be very careful with this kind of layout to understand how this will work, if we'll not overheat or just destroy the structure. And we also have the voltage drop, which tells you how big is the delta between specific points. So this is a very simple tool on one hand, on the other hand, very powerful to understand the current densities and also the voltage drops on your design. More advanced tool is the power distribution network tool, which takes into consideration this frequency ranges and the frequency mode. So it is analyzing the network parameters. So it gives the information about the Z parameters. So you can observe the impedance of a specific power net seen from the specific pin of IC. So from the pin number 16, L16 of U1, we can see this kind of impedance profile. And then we can easily compare it to the target, which was set by the vendor of this microprocessor. We can see we do not fit this requirements, and we would need probably to do a lot of work with the decoupling capacitors. So easily what you can do in PollEx, you can play with the decoupling capacitors, you can create new cases and just populate the capacitors with a different values of the capacitors. Like, I don't know, we can just create a new case, completely different. And if we'll just zoom in to this capacitor area here, you can see case 1, everything is populated. Case 2, only the capacitors we selected are populated, and so possibly with different values. So you can do this kind of what if scenarios, repeat the PDN analysis, and see the impact of the changes on the decoupling network of your design. Maybe one last thing which I didn't tell in this DC drop, what is also quite interesting in PollEx is that it allows you to get the current density, so the amount of current per cross section of copper, multiply that by the resistiveness of copper, and this way you can calculate the power dissipated by the traces. So you just calculate what we call in physics Joule heating. And this model, it can be then used in the thermal simulation. So if you have a kind of inverter, or you have a kind of connection that can really heat up, even on the copper level on your PCB, so you can really reuse this information forward in PollEx in the thermal simulation. And this is what we will move forward to the thermal simulation. Now I would just open also the pre-configured file just to not lose the time. For the thermal simulation, I opened the pre-configured file because for the parts, what you need to do, you need to apply the thermal model for the components because components needs to show some kind of power dissipation. So we need to read the data sheet and apply. There's 2.8 watts. There is some kind of 110 Celsius degree maximum temperature. There are some geometrical sizes. And also you can apply the model of the thermal resistivity of the component. So what is the junction to case, junction to bottom resistance, or even more sophisticated Delphi model, junction to left, right, bottom, top, and etc., etc. So this 8 resistor model can also be applied here. So with the thermal information for the core components, you can see this thermal model here. We can proceed with the thermal analysis. Thermal analysis is on the edge of the electronics and the mechanical simulation. So we have here a lot of constraints which the mechanical engineers use a lot. So a lot of edge conditions which you need to know beforehand running the simulation. So the gravity, what is the type of the heat dissipation, main type, and some parameters of the materials that dissipate the heat, typical boundary conditions for the PCB board, and also the boundary conditions for a specific components. So if there is a specific component like U1, which uses a convection, and it has also a kind of a heat sink radiator, you can also put here the simplistic parameterized model of the heat sink. So what is the delta between the area that touches the IC versus the area which is dissipating the heat. So these ribs of heat sink, you divide the area of the ribs by the area which is touching the device, and you have, for instance, 300 times bigger heat dissipation area from the chip. So this is a kind of setup for the power for the thermal simulation. And then we can also include the Joule heating from the traces which were analyzed inside the power integrity analysis. So we can include a specific net which was analyzed, and this model will be included in the thermal simulation. And we can just run the thermal analyzer to find out what are the hotspots in the design, where I can see some kind of thermal problems in the design. One thing to have in mind doing this kind of analysis, it's the static analysis. It's like you would take your PCB component, put it on your desk, just connect the power, and this is it. It doesn't have any kind of fancy airflow, air cooling, water cooling, and this kind of stuff. This is quite static analysis, maybe including some types of the cooling mechanism like the heatsink, which I have shown to you, or some kind of simple radiation mechanisms. But this is super powerful if you want to do what we call in ECAD designing like floor planning. I want to understand before I will put 5 BGAs if they are not too close to each other from the power or temperature perspective. If I need to move something and see what is happening, you can also do it even in PollEx, a very simple approach. You just catch the device and move it to a new location and repeat the analysis once more. That takes some time, but yeah, you can repeat the new scenario of the placement of the placement analysis, and you can really get the answer if this system will behave correctly afterwards. Good. So we are landing with this presentation. The last thing which is available in PollEx is the verification mechanism. This is one of the most powerful elements of PollEx. We have a lot of verification tests inside PollEx, which allows you to qualify the design. I know in Altium Designer, there's also a lot of DRC tests. They are pretty easy to use and they can run in the background. This is what we have in PollEx. It's much bigger number of tests, doing a lot of verification on top of your PCB. Also understanding the signal integrity phenomena like the return path discontinuity, some kind of shielding challenges. If you want to check the design against the EMC problems, so the stubs can be detected, some kind of power problems, amount of decoupling capacitors, and etc., etc. So more than 100 rules. And how we see it from Altair perspective, when you do the design in Altium, you probably run the DRC in the background. It tells you while you're drawing what are the mistakes you are making. But afterwards, even before the simulation, you can run this kind of full-blown 120 rules check against the company rules to do a kind of what I will call a sign-off process. So I can tell on the basis of thousands of rules, they cannot run in the background because it's too long, but they will tell me if I have made some mistakes on top of my PCB or maybe not, and I'm really ready to perform a more time-consuming and more costly from the perspective of design, more costly simulation in signal, power integrity, and the thermal. So we have some rules that allows you to qualify the electrical design. So these are the DFE rules. We have also some rules that allows you to qualify your design against the manufacturability. This is mainly used by the teams or the companies that are doing high volume production. So this kind of outline regions, cutting regions, drilling, screw holes, and most of this kind of stuff, collisions. So there's also plenty of rules for flex PCB, the flex regions, the flex angles, and etc. And we also have the group of the assembly rules. but for that you need to import the 3D step models for many of these components. So you can also work and find out the body-to-body collisions, or if you use a high volume production, you probably have the visual inspection at the end of the line after pick and place and soldering to find out if you have no tombstone effect or there's some kind of popcorn effect on the solder joint. So not to hide any solder joint behind the huge components for camera vision, you can also, for instance, check the shadowing region analysis on top of your PCB. After the analysis, PollEx provides the interactive report. Sorry for that. Let me just run this analysis for one of these examples to show you how this looks like. Okay, start checking. And what we will get an interactive report on top of the PCB that will show us where is the problem inside of our PCB. There is a trace which has an opening inside the ground. So this is return path discontinuity problem. One more thing which is here, it's also a link to ECAD. It can be configured. This board I just opened from my hard drive. It was not going from Altium Designer directly, but if we will go the full path, spend the time on model setup and all of that stuff, we could click here, link to ECAD, and automatically we should, it even works for this board, we should see the same area in the Altium Designer just to fix the trace inside the Altium Designer. Because, and that's the true for each and every simulation tool, simulation tools does not allow any changes for the layout. Layout is owned by the ECAD engineer. Altium Designer contains the golden data for the layout, and in 99% of the companies, no one will allow the simulation tool perform any changes or do any changes to the layout. So we also follow this rule. We think that this would be a source for multiple issues and errors if we will allow the simulation engineer impact the layout. So there's a linkage to ECAD tools, but there's no possibility to change anything inside of the PollEx. Good. And the last thing which I would like to show you is the possibility to download the models for PollEx. So this is possible through Ultra Librarian. So this is a web page where you can really search for components, electronic components. Let's pick up one of these. So we have the schematic cell, you have the view of the component, you also have the footprint. If you will click to download, you will see that there is Altair, and you can easily download PollEx, some other models for the other Altair tools like SimLab, and you can just get this package on your hard drive and just use it inside of PollEx, just being ahead of some questions that are pretty often asked, where I can find the models, the components for PollEx, IBIS files, step files, or the footprints. So this is how it works. Inside of this kind of folder, what you will get, you have the guidelines, how to install this kind of models. So how to proceed installing the model into PollEx, and you really have some kind of models. UPFX, it's the native format of PollEx, which holds the information about the components and step files. It's the typical mechanical drawing and description of the component. Great. There are also some kind of review tools inside of PollEx which you can use. There's a collaboration. So the red mark tool, but this is some solution that I think you know from Altium Designer, and you will probably use it in Altium Designer. This is used more by the bigger groups of simulation engineers, that you can mark any area of the PCB board just when you do the review, I don't know, fix a connection, and you can just add some area on top of the board, assign some files, data sheets, some hand drawings, and just create a list of the violations found on the PCB board, then pass it to another person which is fixing the problems, like the ECAD engineer, and he can follow the list and do the bug fixing. So this is one other option inside PollEx. And maybe one last thing, which is maybe not in here, but it's in a different area of PollEx, is the comparison of the PCBs, of the versions of PCBs, which might also be quite useful for some of you. So if you have PollEx, there is a PollEx compare functionality within PollEx, which allows to compare two versions of the PCB. Oh, I see it's just limited to the other screen. Let me stop sharing and change the screen. Okay. So this is the tool. You can just read in PDB a binary file, so or the Altium file or the any other file for the comparison the two PCBs, and we can read in another file, and PollEx will just compare these two PCB versions and can really tell what are the differences if we have in one version of PCB capacitor C157 mounted, in the other version not, if we changed any kind of routing, if we change any kind of parameters, like here C157 in this PCB it's mounted, in this one it does not exist. If we change any kind of routing, it will also show us maybe someone changed the connection to the address pin due to make it the layout easier, or due to the limitations of the space. So this is how PollEx works. It can also be merged into one PCB. Also some kind of parameter changes. Good. We are 10:15, so let's leave 15 minutes for the questions. So I will stop here. I hope you enjoyed this kind of tool, and you will see it as a very useful one for your everyday job.
Thank you, Marek, for a very nice presentation of those capabilities. So this is from the technical part. A nyní bych předal slovo panu Čurdovi, který by to celý uzavřel, než se pustíme do otázek.
Děkuju za slovo, děkuju ještě jednou Markovi za, já myslím, velmi pěknou prezentaci a taky jako názorné vysvětlení, co PollEx představuje. Určitě jsme neviděli všechny možné funkcionality, bylo to jenom nějaká část, co se vešlo prostě do tohoto časového rámce. Proto tady v tom shrnutí začnu spíš takým kontaktem na nás. Když budete mít jakékoliv dotazy po tomto webináři, tak jsme k dispozici, buď se můžete obracet na mě, nebo na náš support for advanced engineering, takže HV support, HV jako Hyperworks support, což Hyperworks je simulační platforma od Altairu. Můžete vyrazit i na supportní web Altairu. To je tato adresa. Marek ho ukazoval, jsou tam tutoriály, příklady, znalostní báze, poměrně dost informací. Je to i místo, kde si můžete zažádat o trial licenci. Já bych spíš doporučil se na tu trial licenci obrátit na nás, protože my pak ji umíme snadněji prodloužit, když by bylo potřeba, takže je to takový flexibilnější. ale jsou obě možnosti. A kdyby vás zajímalo vlastně, jak to je s licencema PollExu, tak existuje několik možností, nebudeme si je tady asi všechny vysvětlovat, ale to nejjednodušší je, že je prostě nějaká jednouživatelská licence, buď nějaké varianta Basic nebo Advanced, my jsme se dneska koukali víc na ty Advanced funkce, ale existuje takový flexibilnější balíček za pomocí licenčního systému Altair, to je takový ten pomocí licenčních jednotek, kde v rámci té licence můžete použít různé typy nástrojů. Byly vyjmenovány vlastně na tom úvodním videu, když jste tam viděli, jak se staví ten dron, tak vlastně všechny ty disciplíny, které se zapojovaly do toho ověřování toho návrhu, ať už to bylo PollEx jako takový, systémový modelování, návrh elektromotoru, návrh čipů, návrh vlastně napájení, takže všechny tyhle ty simulace vlastně pod jednou licencí, kde vás jako nenutí Altair vlastně kupovat si prostě každý nástroj zvlášť, ale za jedny peníze, jakoby máte celé to spektrum. Tyhle ty flexibilní licence mají ještě tu výhodu, že můžou být roční, trvalý nebo i dokonce i krátkodobý, takže si můžete po dobu projektu nějakým způsobem třeba ten rozsah licence navýšit nebo jak je potřeba. Tím asi nebudu úplně zabíhat do podrobností a spíš nějakým způsobem něco nabídnu. Jsme rádi, že jste se zúčastnili dnešního webináře a že máte asi zájem o tohleto téma. Takže proto, kdo by se do konce letošního roku pro ten PollEx rozhodl, ať už jakékoliv licenci, která se ho týká, tak máme tady nějaký promokód, který vám asi přinese nějakou slevu na nákup, je to 10%. Takže když tak si ten promokód opište a využijte ho, máme na to dost času. Takže to je takový jakoby příspěvek za nás, pro vás, účastníky dnešního webináře. Takže pojďme na dotazy. A já zase předám zpátky.
Děkuju. Chviličku. Tak, dotazy už se nám tady, jeden už tady máme. Já bych ještě vlastně vás požádal, než nám začnete utíkat, o zpětnou vazbu na náš webinář a k dotazům. From Mr. Parkman, hello, thank you for interesting presentation. I apologize if this has already been covered, as I wasn't able to attend the entire session. Could you please compare your tool with hyperlinks? Thank you.
Okay, that's a really good question. Hyperlinks is better when it comes to the higher frequencies. I have shown you that Altair PollEx is a full 2.5D simulator, so it's limited to the speed of 1.5 gigahertz, maybe a little bit higher. Hyperlinks is of course 2.5D, but it also have this Nimbic solver behind, and it also have multiple other 3D electromagnetic solvers that are used for the custom shapes on top of the PCB, like teardrops, specific pads, antipad of the via, etc. So hyperlinks will give you the good accuracy for much higher frequencies. It will go to probably, I think, 20 gigahertz easily. So it's much higher in the frequency, but also you have to compare the price. How big is the gap between these two tools? This comes, of course, with this frequency range. But on the other hand, PollEx, its power is more in the verification and qualification of the PCB. In standard hyperlinks gigahertz, you don't have it. It's split in the mentor tools between hyperlinks DRC and Valor. In PollEx, it's under one umbrella for the PCB. Everything is there. and it's very easy to learn and configure. So it's just a couple of days to run your first tests, and also signal integrity simulations for simpler circuits, simpler solutions. It's much faster in Altair PollEx. Hyperlinks, it's very professional tool. Altair PollEx, it's dedicated for a smaller groups, smaller companies, people that needs to jump in and out to this tool and use it from time to time. So they are somehow complementary. If you have super deep experts for, I don't know, DDR4 or 5, you probably want to use hyperlinks. I would not cheat you here. But if you have lower frequency links and you have a standard DKD engineer that needs to jump in for simple simulation and go back to layout, I think Altair PollEx is much better choice here. So that would be my let's say high level comparison between tools.
And maybe if I may extend it, or how I understand it, the basic principles are the same for both tools.
Yeah,
like you extract the parameters of the connection, and you do simulation on this extracted model of the connection. So in this respect, it's the same, but it means they have some corrections for special cases for higher frequencies. Yeah.
Correct.
Okay.
Yeah, exactly.
Okay.
Yeah.
Okay, so that's done. And we do not have more questions than this one. Just we will wait like 1 minute if there's something more what will appear.
We are also maybe on the same question. We are also working strongly on implementing 3D electromagnetic solver, like you have seen FECO for the antenna design and the other topics. We are integrating multiple tools together to get this functionality in PollEx, but I cannot tell you what is the release date for the complete solution. You can understand it's a lot of headache and a lot of tests that needs to be done before we'll release final version. But it's on our roadmap, and it's very high level topic on our roadmap, so it will quite soon come. The first one will come with the power integrity solver. Somewhere at the end of this year, you will see a lot of improvement the power integrity side. Then the signal integrity with full-blown SerDes solution will come. So this is ongoing.
Perfect. So it means that, at least in my understanding, PollEx is currently focused on like general PCBs, like those which are usually done by our customers, and then you need something special like high frequencies. It's not the focus of the tool.
At this point of time, yes, I would agree.
Yeah. Okay. We have received the feedback here, and the question from Mr. Kralicek, is CADI tool for checking the schematics part of the package?
Yeah, so this is a tool which is super interesting. I know what you mean. KD Solutions is the tool that is under our APA. This is Altair Partner Alliance. So this is the tool. It's the online tool that you can use. And Altair Partner Alliance works like this, that under some groups of licenses, you can use the third-party tools with the Altair licensing. So we can use Altair licenses to open the KD tool. And the KD tool is the tool to inspect schematics with artificial intelligence. So it allows you to read in the parts of your schematics and also the data sheets. I will not run it right now, but it also then analyze your schematic against the issues which comes from the datasheet. So the datasheet tells you that you need to use 10 picofarads for the 8 megahertz oscillator. If you forgot that, So the KD tool will tell you, yeah, for the pin number 25, according to datasheet, you need 10 picofarads and you use 6 picofarads, etc., etc. So the mistakes on your schematic compared to the datasheets. So this is KD, and somehow the answer for that, I would go to Tomasz to ask him if your package that you have in your company contains the APA, so Altair Partner Alliance Tools. If not, sometimes you need to extend the package with these capabilities.
Okay, thank you. And that's it for with questions for now. Yeah, we can end our poll for the general feedback. Here you can see the results. So we did quite good. And if you have no more questions, we can wrap up this session. Děkujeme vám za pozornost. Tady jsou kontakty na nás, na všechny. Co se týká nástrojů Altairu, tak nejlepší se obracet na pana Čurdu. On už vás navede nebo vám zařídí odpovědi, vlastně, které se tohohle týkají. Za nás to vlastně byla takové další pokračování k naší sérii ohledně simulací, kde jsme pokryli obvodové simulace, a jelikož Altium Designer nemá přímo možnosti na simulace plošných spojů, tak jsme se obrátili takhle na kolegy, kteří nám ukázali, co je možného v nástrojích, které spolupracují s Altium Designerem, a jak jste viděli, skrz extension se ty informace tam dají dostat, a Marek vlastně říkal, že ten extension se toho bude učit časem i víc, takže ta spolupráce bude těsnější. Děkuju za pozornost, mějte se hezky a budu se těšit na dalším webináři.
Děkujeme taky.
Nashledanou.
Ano.